Hello, everybody. Good evening and welcome to the Sigma meeting for March 2023. Let's start off. Those who don't know me, I think we have some first-time visitors here again tonight. My name is Pete Sherman. I'm the chairman of Sigma, and I will be your MC for the evening. I want to welcome those people, the first-time visitors and new members, especially, but also our affiliated club members too of Highland Astronomical Society, Aberdeen Astronomical Society, Cairngorms, and also North Ronaldsea. If you're here tonight, you're all very, very welcome. Okay, helping me in the background, I've got Rich and Mick, who are the Zoom co-hosts, so if anything goes wrong with me, they will cut in and take over. They're poised to do that. Mick will also be doing the Moray Sky at Night in the second half. Rich will be handling the questions and answers, and Tim will be doing the vote of thanks. And I say Ray is here as well. He's going to be doing the members' photos tonight for a change. Gives me a break. So for anyone who hasn't used our Zoom system before, this is just how we sort of. I'm just going to go through how we how you can ask questions to Patrick. The way we do it is you'll see in the little toolbar there's a Q&A button. If you press that, and you can put questions in there at any time you want to throughout Patrick's talk. And Rich will then pick them up at the end of his talk and ask them over to Patrick there. Don't go putting your questions in the chat because it will get lost in the chat. As I say, Rich can't handle watching the chat and the Q&A at the same time. Just too much for him. Too much for anybody, to tell you the truth, not just him. So you'll see the chat function is there. If you want to talk to talk to the other people who are in the room, then you can do that by clicking the chat button, but just make sure you change the drop down box to everybody, otherwise it just comes through to us panelists here. Okay, that chat will actually be turned off during the main talks because it gets a little bit distracting when you keep getting these pop-ups coming up and the speaker's trying to do his presentation. Right, okay, so this is how we run our talks, our meetings, sorry. Basically, we'll have a main talk tonight from Patrick Barth. So Rich will be handling the Q&A. We then have a little 10-minute break. It gives us time to get set up for the second half. And I say Ray's going to be doing the members' photos. They've got some fantastic photos in there and quite a few of them, so please stick around for the second half. You'll be disappointed if you miss it. And then I'll be doing a little bit of club news to finish off with. We look about finish around 9:30. Okay. So our speaker tonight, Patrick Barth. Patrick is originally from Germany. He has a bachelor's and a master's in physics, and he got that from the University of Heidelberg in, I think I said that right, in Germany. During his master's, he spent a year abroad in the University of Washington in Seattle. In 2019, he started his PhD at St. Andrews in astronomy and earth science. In 2022, he moved to Austria to complete his PhD at the Institute of Space Research of the Austrian Academy of Science in Graz, which is where I believe he's joining us from tonight to give us an insight into what makes planets habitable. I'm sure this is going to be an interesting and intriguing talk. And I want to thank Patrick. I want to thank you very much for coming and giving up your time for us. And I will hand over to you now, and you can start your screen share.
Thank you very much.
Okay, we've got you. Over to you.
Perfect. Yeah, thank you very much for the introduction. It's very nice to be here to talk to you remotely from Austria. I'll just skip over this because after your nice introduction. And tonight I want to take you on a journey through the solar system and beyond, and to look for what makes a planet habitable, where we find habitable environments in our solar system and beyond, and how we can find habitable conditions in exoplanets and maybe even life. We'll start this tour at our home base, planet Earth, and then look to our neighbors, Venus and Mars. Then we'll move out to the outer solar system, to the gas giants Jupiter and Saturn, or more precisely to their icy moons. And then we'll leave the solar system for the last bit to look at the wide diversity of exoplanets out there. Okay, so what is habitability? Habitability is the ability of a planet or a satellite, for example, a moon, to harbor and sustain life. So this means, in theory, life doesn't need to be able to start on a planet that is habitable. So we can also look for a habitable planet where, for example, that would mean that our species could travel there and live there. And there's one factor that is very important for habitability, at least for life forms as we know them from Earth, and that is liquid water. And so I'll mostly spend this talk talking about conditions that allow for liquid water to be present, and therefore for life to be present. And what determines that we can have liquid water on the surface of a planet are a lot of different factors. It starts with the star, because it's the radiation of the star that is heating up the planet, but it's also the radiation from the star, especially the X-ray and UV radiation, that can strip the planet of its atmosphere. So the size and luminosity of the star are very important on the evolution of the planet. Then it's the evolution of the planets depends on in what kind of system it's situated. Are there other planets, smaller planets, larger planets, with which it interacts during the billions of years of the system's lifetime? Or if there are any moons of the planet. And then there are a lot of factors of the planet itself that determine whether it can have liquid water on the surface. Most importantly, the mass and the radius of the planet, which then determine also what kind of atmosphere it has, the position in the solar system, in the stellar system, so the semi-major axis, the distance between the star and the planet, determine how much radiation it receives, and therefore the surface temperature, which is also depending on the atmospheric composition and the atmospheric pressure. And then the interior of the planet determines whether the planet has a magnetic field that can protect the atmosphere of the planet from charged particles, or if there are plate tectonics that recycle the atmospheric material and therefore keep the carbon content, for example, at a habitable level. And over the next 45 minutes or so, I will discuss quite a few of those different points and using examples in the solar system and beyond. So, but let's start on the planet, the only habitable planet that you know of, and that is Earth. Earth is located in the habitable zone of the solar system, which means that the radiation that it receives heats the surface of the planet to a temperature where liquid water is possible. If it's closer to the star, it would be too hot. And if the Earth were further away from the star, it would be too cold. Venus and Mars are at the edges of this zone, which means that if they had slightly different or quite a bit different atmosphere, they might have had liquid water themselves. But how did life actually start on Earth? We actually don't really know it yet. but there are a few different theories. One is that life started at deep sea hydrothermal vents. Another theory is saying that life started in warm little ponds on the surface, or that life was delivered to Earth. This is so-called this panspermia theory. For the hydrothermal vents, the idea is that you have these porous structures of porous minerals on the surface of the ocean, where there's a lot of hydrothermal activity in the surface. And then hot gases are released into the ocean, and inside of this porous material, you'll have a very different environment than outside. You build those natural gradients in temperature and pH. And these pores will then eventually develop into the first protocells. Darwin's warm little pond assumes that somehow we produce organic prebiotic molecules, which then assemble in these little ponds, concentrate and form longer molecules, such as RNA and DNA. But somehow we need to deliver these materials in there. And one theory is that lightning is responsible for this. There were some really famous experiments in the 1950s where two scientists inserted electric spark into a reducing gas mixture. Reducing means it's made up of methane, ammonia, and hydrogen. They connected this flask to some water reservoir, which basically resembles the warm little pond, and waited for a week and found more than 20 different amino acids being produced. Now, the problem is that we now know that the early Earth's atmosphere wasn't reducing. It was more likely to be a combination of CO2 and N2 rather than methane and ammonia. So in order to now still use this idea of producing organic molecules from your atmosphere via lightning or other high energy impacts, you need to produce or create a reducing atmosphere locally or for a short time, at least. And places where this could happen is in the plumes of volcanoes, which are determined, the gas composition is determined by the composition of the planetary interior. And so it might be very different from the surrounding atmosphere. Or we could have meteorites that impact the Earth, bringing a lot of iron with them, which binds the oxygen in the atmosphere, making the atmospheric compositions, at least for a short time, more reducing, allowing for more organic molecules to be produced. But the most logical explanation, or the most used explanation right now, is that organic molecules were delivered. Prebiotic molecules have been found, for example, in cometary ices, and then they are delivered into these warm little ponds, which undergo cycles of heating and precipitation and evaporation, and therefore allowing those molecules to concentrate, bind together, and form longer chains of molecules, and eventually RNA and DNA. Okay, but this was just a very short excursion on the origin of life. Let's go back to the planets in our solar system, and let's start off with Mars. Mars is a very interesting planet and has been visited many, many times by various different missions. Here you can see Perseverance, which is the latest NASA rover. And Mars has been in the news over and over the last years and decades with claims that water has been found. And actually there is some liquid water on Mars underneath the polar ice caps, or multiple photographs of such ridges have shown that water seems to be trickling down in those black lines here. So some liquid water, probably with a lot of salt to make it liquid at those cold temperatures. But if we go back in time, we believe that Mars was actually much more water rich, with oceans and rivers and streams. Because if we look at these geological features, they remind us of what we find on Earth as well, like canyons, sediments, river deltas. So we believe that Mars billions of years ago had actually was a temperate planet with a relatively thick atmosphere and liquid water, and maybe even life. So the question is now, what happened? And the problem that Mars has is that it's smaller, so it has a lower gravity than Earth, and therefore can't hold on to its atmosphere with the same strength that Earth can. And it also doesn't have a magnetic field, at least not anymore. And the magnetic field is very important in redirecting charged particles that the sun emits constantly, especially during solar flares, and which strip away the atmosphere from the planet. So that's what happened to Mars, and that's why Earth still has a thick atmosphere. If we now look on the other side of Earth, to Venus, we find something completely different. The atmosphere now is much thicker. We have a pressure at the surface of more than 90 bars, a temperature of 460 degrees Celsius. So we could melt lead there and definitely bake some pizzas if we ignore that it is raining sulfuric acid. Also, the atmosphere is made up mainly of carbon dioxide. So it's really not a place where we would want to be, and definitely not where we'd expect life. But also for Venus, there's a theory that Venus might have looked like more like Earth in the past. That it was covered by oceans at temperate temperatures, but then the high CO2 concentration in the atmosphere would make it heat up more and more until all the water evaporates. And eventually it enters this state, this runaway greenhouse state, as we call it, with a thick steam and CO2 atmosphere. And it is basically in like a bit accelerated and larger scale what's happening on the Earth right now with increasing CO2 concentration and global warming. But this is also still only a theory. There are other theories that say that Venus never had liquid water on its surface. Now that's even more interesting that a few years ago now, there was a detection of phosphine, pH 3, in the clouds of Venus. There was a little bit of debate about whether this feature is actually correct, or if it was maybe much less in abundance than the first measurements suggested. But it's still extremely interesting because we wouldn't expect phosphine to be in such an atmosphere. We know that phosphine is abundant in the atmosphere of Jupiter, but that atmosphere is dominated by hydrogen and helium. Venus' atmosphere is dominated by CO2. So what we would expect is that phosphorus would be more in the form of PO2 rather than pH 3. So either there is some novel chemistry that we just don't know on Earth, or it is actually produced by life. Because the only place on Earth where we find phosphine is in anaerobic ecosystems, for example, the intestines of penguins. But if there is life on Venus that produces phosphine, where's this life? And the detection of phosphine actually tells us where we have to look, because we find this phosphine in the cloud decks. And in the clouds of Venus, we actually have an area between 50 and 60 kilometers height, where the temperature is like right for liquid water, and the pressure is around 1 bar. So again, if we ignore the sulfuric acid rain and clouds, actually perfect temperate environment for life. The theory behind this life cycle is now that we have some spores that are dried out and inactive, very light. They're being transported upwards by the airflow into the clouds. They merge with water droplets in the clouds, which activates them. They can grow, they can replicate. And eventually this droplet gets too heavy. and falls again until the water evaporates and the dried out spores start to rise again. Now, this life cycle can't explain, or these conditions can't explain how life could have formed on Venus. So this only works with if either Venus was more habitable at the beginning, and then life just ended up at the only spot on the planet where it's still, the temperature is still correct, right for life, or life was delivered from another planet, for example, from Earth, and then just was seeded in the cloud deck. Okay, but now let's move on to some more bit colder habitats. The icy moons of Saturn, Enceladus, and Jupiter, Europa. These moons are extremely interesting because they are covered by ice, with a relatively thick ice layer on the outside. But because they are interacting with the tidal forces of their host planets, Jupiter and Saturn, they get heated quite a lot from inside. And that means that between the ice and their rocky core, they have a thick, thousands of kilometer thick ocean, water ocean. And particularly the Cassini-Huygens spacecraft, which was in Saturn orbit for more than a decade, made detailed studies of these oceans of Enceladus. And so we know quite a lot about their structure, and particularly about this special feature on the South Pole, these jets of water ice that come out of cracks in the ice layer. So what we think is happening here is that on the bottom of the ocean, at this point, you have hydrothermal vents powered by hydrothermal activity underneath in the rock. So very similar to what we have in the oceans on Earth. And they are heating the water up there enough to make the ice a bit thinner there, allowing for these cracks to open and water to be ejected into space. And Cassini actually managed to catch some of this material and analyze it. And they found methane in this plume. And there was a study a few years ago that suggested that the origin of this methane is life, or as like this, their second most likely option, it would be that it is in habitable conditions. So either life, directly life, or no life, but habitable conditions. So this is probably one of the most exciting places we want to explore in the solar system on the search for life and habitable conditions. But it also means it's a very precarious system. So if we send a mission there that will land on Enceladus, drills into the ice and goes into the ocean to search for life, we need to make absolutely sure that the spacecraft we are sending is sterile. Because if there are really habitable conditions on this planet, any life that we bring, and if it's just a few microbes on the shell of our satellites, can seed life there, and we might be then detecting life that we introduced rather than that is originating on this object. There's another very interesting and a bit special object in the solar system. It's another moon of Saturn, Titan. Titan has a thick atmosphere, a thick nitrogen atmosphere with organic hazes, which make it look like this opaque yellow color. And the surface features are very similar to Earth. So we have pebbles, we have lakes, we have dunes. But the surface is made of ice. And underneath this ice, there's also a thick water ocean. So we have water ice, surface water ice pebbles. The sun, the dark material you can see in this photo on the left here, is actually from those organic hazes from the atmosphere that precipitated down. And instead of water lakes and water cycles, water rain, you have liquid methane present. and it's extremely cold at -180 degrees Celsius. So we are also sending a mission to this place, a huge dragonfly that will be able to fly between different spots on this moon. And here we might be looking for something that is very different from Earth. And so we might be looking for life that is not dependent on water as a solvent, but liquid methane. And that would mean it's also a completely different chemistry and very different from what we can just imagine here on Earth. Okay, so if we look back onto this diagram, only by looking around at the different places of the solar system, we've seen quite a few places where there is liquid water. So we found liquid water, obviously, in the oceans of the surface on the Earth, but also in the subsurface oceans of the moons of Jupiter and Saturn, which are heated by the tidal interactions. We've seen that the presence of a magnetic field will determine whether or not a planet can keep its atmosphere. And we've seen that we can have liquid water or habitable conditions, maybe not on the surface, but up in the cloud layers of a planet. And now I'm going to take a step from the well-known, or at least to some extent well-known field of the solar system onto the huge diversity of exoplanets. I'll first shortly introduce you how we can detect exoplanets. There are four main detection methods, and the most used ones are the radial velocity method and the transit method. For the radial velocity method, we use the fact that when a planet moves around its star, it's not just the planet moving around the star, but it's also the star moving around the planet. Or more precisely, both of them are moving around the common center of mass. So in the case of the star, this is only like a wobble on the spot. This wobble of a few meters per second is enough to squeeze the wavelength of the light when the sun, as the star is moving towards us, and to stretch the wavelengths when the star is moving away from us. And then the light seems a bit bluer and a bit redder. And we can measure this and then detect the planet by this change in color. The transit method is maybe a bit more intuitive. We just look at the star, measure the brightness of the star, and when we see a periodic dip in brightness, we can assume that this is a planet and measure its radius. This is particularly interesting if we have both a radial velocity and the transit measurement, because then we get the mass and the radius of the planet. Microlensing and direct imaging are less used methods. For microlensing, we are using a star that is moving in front of a background source, so another star or galaxy. And the star in the front will then bend the light from the source behind. And if it's just the star, it will be symmetric on both sides of the planet, or on all sides of the planet. I'm sorry, about the star. But if there now is a planet orbiting the star, then the deflection won't be symmetrically anymore. And this asymmetry we can measure and detect the planet. And direct imaging will block out the light from this star and then can spot actually the planets around it. But that only works for pretty large planets that are far away from their host star. So far, we found more than 5,300 exoplanets. I double-checked that number this morning. And they have a huge variety of masses, of radii, of distances to the star, stellar host types. Here are some of them in a diagram with their size on the y-axis against the orbital period in days on the x-axis. So Earth would be at 365 days, somewhere here, and 1 Earth mass. So you can already see that there aren't many planets that are similar to Earth that we found, in a sense that because it's hard to detect small planets that are far away from the star. A lot of the planets we found are giant planets that are very close around their host star, because that's just the easiest. The closer your planet is to the star, the more area it covers, for example, for the transit method. And those hot Jupiters are therefore very easy to detect. Then we find cold gas giants. These are similar to Jupiter and Saturn. And then we have actually found quite a lot of Earth-sized planets. They're just usually around different types of stars and much closer to the star. It's even so close that they have a molten surface and actually lava worlds. And then we found a lot of planets that are in between. Some of them look maybe a bit like Uranus, Neptune, if they were able to keep a hydrogen-helium atmosphere. Others might have lost this atmosphere and have a thick ocean covering the rocky interior. So they might be looking like scaled-up versions of Europa or Enceladus. The planets we now are looking for habitable planets are those rocky planets, and not including the lava worlds. So let's zoom into this area and in a bit of different diagram. So here I'm showing you now on the x-axis the flux that the planet receives. So 1 means it receives the same amount of flux of light or of energy that the Earth receives. So Earth is up here, orbiting the Sun, which is a G star, and has a temperature of nearly 6,000 Kelvin. So this is the temperature of the star on the y-axis. And the dots are all different planets. We're not interested in the gas planets, so the white and yellow dots. We're interested in those blue small dots. These are Earth-sized planets. In particular, in those that are orbiting in this green area around their star, which is the habitable zone. So where we could expect them to have liquid water. And you might already notice that most of these planets, of these blue dots in the green zone, are in this lower quarter of the plot, orbiting M dwarfs. And this is due to two factors. First, there are more M dwarfs. These are the most abundant stars, and so we'll also find more planets around them. And they're smaller, and so the planets are closer in and therefore easier to detect. Just show you a few famous examples of those planets. For example, Proxima Centauri B is a terrestrial, so Earth-sized planet orbiting such an M dwarf. And it's the closest exoplanet to Earth, orbiting the closest star. So this is our direct neighbor. And then the really interesting TRAPPIST-1 system, which consists of 7 roughly Earth-sized planets. And 3 of them, or 4, depending on the definition, are orbiting the star in the habitable zone. So this is a really, really exciting system. And there have been a lot of studies about, and we'll come to this in a moment again. And I mentioned that all these planets are orbiting M dwarfs, and M dwarfs are dimmer and cooler than, for example, sun-like stars, which are called G stars. And because they are dimmer, the habitable zone, so the zone where liquid water can be present on the planet, is closer in. And this comes now with a few negative side effects. First, if a planet is orbiting very close to its star, it will be tidally locked. This is the process that also happened to the Moon, because it's orbiting relatively close to the Earth, and the tidal interactions between the two pull it such that it faces the same side to the Earth at all times. And that's the same that will happen. That's happening to planets orbiting close to the host star. And so you might have a planet in a habitable zone, maybe even with the atmosphere that is supporting liquid water on the surface. But it might be too hot on the day side because it's always irradiated by the sun or the star. And it might be too cold on the night side because it never gets any light. So you might have an ice desert on one side and a hot desert on the other side, and might end up only with a strip of habitable area around the terminators. Another problem facing planets around M dwarfs is that M dwarfs are the most active stars. So they produce a lot of XUV, so X-ray and UV radiation, a lot of flares, and therefore a lot of charged particles. And because these planets are much closer in, they will get a lot more of this radiation. So even if there are a lot of planets in the habitable zones of M dwarfs, they might actually not have much of an atmosphere left that could temperate the surface temperature. So how do we now determine whether such an exoplanet is habitable or not? For that, we have to go through a lot of iterations of reading studies, learning physics, chemistry, geology, writing models, simulating codes, drinking a lot of coffee, and repeat this over and over again. Now, just have going to show you now one example, one overview. So we can't just look at a single snapshot. We can't just look at how the planetary system is looking right now to determine whether it will be habitable or not. We have to take into account the whole evolution of the planet. So we'll have to start with under which conditions did the planet form? How did the gas and dust cloud look from which it formed? Which composition did it have? Then how is the mantle and the core separating out? What is the first type of atmosphere that is outgassed? It's usually made up of hydrogen and helium or water. Then this atmosphere is eroded away by impacts, but also by the X-ray and UV radiation. So we also have to look at how is the star evolving at the same time as the planet. Then at some point, the interior, the mantle will solidify. We start to outgas a secondary atmosphere, which would then made up of nitrogen, CO2, maybe methane. This atmosphere will be then again eroded by maybe some late accretion of material, where meteoroids hit the planet millions or billions of years after it's formed. And eventually we end up with some sort of mantle behavior. For example, plate tectonics, which will then also recycle the atmosphere. So just going to show you one example of the TRAPPIST-1 systems, how we go about to find out or to test whether these planets or what atmospheric composition these planets might have. So we know from observations that these planets have a very high water content of 8 to 18%. This is like thousands of times more than water than the Earth has. So that's really, really water rich. But depending on when these planets got their water, received their water, changes the outcome of their atmospheric evolution. So we ran models to simulate the magma ocean phase of those planets. So this is the phase where the planet is still molten. The mantle of the planet is still molten, which means that the water that is in your atmosphere will dissolve into the interior, but it also will be eroded away by the radiation from the star. You will lose a lot of hydrogen and also some oxygen, but most of the oxygen will remain on the planet. It will also dissolve into the interior, but at some point it will build up in the atmosphere. So if you start such a planet with a lot of water, you'll end up with still quite a substantial amount of water, but also hundreds of bars of oxygen in the atmosphere. But if we want to avoid having these large amounts of oxygen in the atmosphere, we could imagine that the water is not on the planet from the beginning, but it is delivered at a later point when the planet solidified, when the star calmed down and the radiation from the star is not as strong anymore. But actually, this TARP-1 system is very unique in a way that all of these planets are orbiting their host star in resonance, which means that, for example, while planet E orbits the star 3 times, planet F orbits the star only 2 times. And this is a very tightly packed system. And if you change one of these elements, the whole system might break down. So this allowed us to estimate how much mass you can throw onto one of those planets before just all those input of kinetic energy will break the system apart. And we've figured out that to explain the amount of water that these planets have, you'd have to throw more material on there than would be allowed before the chain breaks apart, which then in return tells us that the water must have been on those planets before, and so they should likely also have a lot of oxygen in the atmosphere. And now we can go on and run simulations for every point in this diagram. You might now ask, is there an easier way? Like, can we avoid running simulations and calculating all the possibilities for every point in this diagram and every corner and every decision in the evolution of a planet? Well, we can look for our penguin intestines. We can look for so-called biosignatures. Biosignatures tell us that life is present on the planet. And if life is present there, it must be habitable. So how do we find biosignatures? For that, we use again our transit method, but now instead of just looking at the overall brightness of the star, we look at the brightness in different wavelengths. And now if the planet has an atmosphere, the gases in the atmosphere will absorb some of the light at certain wavelengths. And at these wavelengths, the planet will then appear larger. And at other wavelengths, the atmosphere will just let the light through and the planet appears smaller. So if we were to take such a spectrum of an Earth-like planet, we would get this. So all those gaps in between here, this is basically the light just passing through the atmosphere without being stopped. But whenever there's a peak, light is absorbed by some gas in the atmosphere. So at this wavelength, for example, it is absorbed by ozone. Here we have a lot of absorption from carbon dioxide. Then we have a lot of water features here, and then even some methane absorbing radiation from the star. And if we were to observe a spectrum like this would be a smoking gun. There's no question. We have methane and CO2 and water and ozone. Sure, there's life. But usually we can't, we don't get all of these gases. And we also don't have the resolution power to take such a detailed spectrum. So we need to pinpoint, or we try to pinpoint, a few individual gases that we can say, okay, if this gas is present, life must be present. And the first one that comes to mind is oxygen, because oxygen is on Earth the most abundant gas that is produced by life. And if we see oxygen or ozone in the combination with the gases we see on Earth, well, that's pretty clearly life. But we've seen that we can also produce a lot of oxygen just by removing hydrogen from the water on the planet. And we might end up with very thick oxygen atmospheres that are just totally not habitable and definitely not produced by life. So oxygen is a slightly difficult biosignature. Another one is nitrous oxide, N2O. N2O on Earth is produced by life. But there are also processes that produce N2O that are not life. For example, lightning. Lightning in an atmosphere that has a lot of CO2 or oxygen produces nitrogen oxides, NO, NO2, and also N2O. So one idea to still try to use N2O as a biosignature would be by looking if we see other lightning signatures. So if we see also NO2 and HNO3, this would suggest that lightning is the origin of the N2O rather than life. And I'm actually currently working on a project where we're trying to figure out how much N2O and how much NO2 we get from lightning in our atmosphere, and whether we can actually use the combination of both to see that we actually not have a biosignature. Methane is another biosignature. Methane is the first product of life on Earth. So before there was any oxygen in the atmosphere, microbes produced methane. But you can imagine to have different conditions where you also produce quite a lot of methane. For example, you could outgas it from the interior via volcanism. You could reduce the atmosphere by the delivery of materials, or you could hydrothermal activity. So maybe it's not so good to look for an individual gas, but maybe a combination of gases. And there we're looking into so-called chemical equilibrium or chemical disequilibrium. So chemical equilibrium means you put a lot of different gases into a box, and then you just wait for hours, days, years, millions of years, billions of years. And eventually those gases will react with each other to produce a state of minimal energy. So if you start with a mixture of N2, O2, and methane, it will slowly react to a mixture of N2, CO2, and water. And that's then the equilibrium state. Life now has the tendency to create a disequilibrium. So it will constantly produce a gas that you would not expect in equilibrium. But because life is just constantly producing it, it will never go completely away. So for example, this CO2 methane combination we had on the early Earth is such a disequilibrium. But if we have outgassing from a reduced mantle, so volcanism into a CO2 atmosphere, we would also expect to see methane being produced. However, we would also expect carbon monoxide to be produced. The whole palette of carbon, methane, CO, and CO2. And that is why CO is described sometimes as an anti-biosignature. Because CO is basically a very easily accessible form of energy in carbon. And so you would expect if there's life present, it would just eat the CO, eat the carbon monoxide. It's the same if you were to go to some physics department and you put out a plate of cookies outside the lecture theater and wait a day, come back the next day. And if the cookies are still there untouched, then you know that there are no students in this building. And that's the same with this planet. If you have CO on there and you see it, it's just present there, you can suggests that there's no life present because life would make use of this carbon monoxide. But even there, under certain conditions, lightning can produce also a lot of CO, and we're currently looking into whether this is enough CO to be detectable. And then again, under certain conditions, you might find methane, CO2, and water in equilibrium, in coexistence without CO. So again, you need to be very careful under which circumstances you might expect various combinations of gases as a biosignature. So, well, is it really easier to look for biosignatures, or is it still very hard? Well, we'll definitely keep looking, and we're doing this with newer and better spacecraft. So, for example, the JWST, which was launched on Christmas a bit more than a year ago, and then in the meantime has produced some really exciting images, which I'm sure you've seen before, and also the first spectra of exoplanet atmospheres. So in this case, they found several water features, so water abundance in the atmosphere of a hot gas planet. So now this is not a planet, of course, where we would be expecting or would be looking for habitable conditions or life. And unfortunately, JWST is not able to observe the atmospheres of terrestrial planets, of Earth-like planets, with the same resolution. So we probably have to wait for future missions, for the next flagship mission, which might be something like those telescopes shown here, either the Habitable Exoplanet Observatory, which would be just dedicated for exoplanets, and where you'd have a gigantic star shield that's flying thousands of kilometers away from the telescope to just block out exactly the light from the star, but not the planets surrounding it. Or Louvois, which looks like a blown-up version of JWST, and would also not be able to observe in the UV and optical, and in addition to the infrared. And it actually might be a combination of those both telescopes that was at least recently recommended in the decadal survey for the next big mission. So I hope over the last 45 minutes or so, I've shown you how exciting, diverse the world of planets and exoplanets is in our solar system and beyond, how many different conditions we have for liquid water or habitable conditions we would expect in all those different habitats. And if you have any questions, I'm happy to take them. Thank you very much.
Hey, thanks very much, Patrick. That was an excellent talk. I've got a few questions here for you, and there's a few coming in on the Q&A as well. First question I've got is, do you think that a habitable planet has to be roughly the size of Earth? You know, because we've got 1G and that sort of thing, or do you think if the gravitational, you know, the planet was so massive that it had a high G, it just wouldn't be able to support life?
So there's a little bit of variation possible, but if you go to, for example, a smaller planet, it will be harder for the planet to keep its atmosphere. You might more likely to end up with something like Mars. And if you go to higher masses, you might start to accrete a thicker atmosphere, maybe even keep your hydrogen helium atmosphere, which would also not support habitable conditions on the surface, because you might not even have a surface, or if it would be probably too hot. So there's still a little bit, you can go to a few Earth masses, but it's not much of a wiggle room you have.
Yeah, cool. Okay. A question here from Ray, and it's basically how close are we to being able to detect atmospheric pollutants, which might indicate industrialization. You know, basically a developing society, not just one with you know, animals on it and that sort of thing, and plants.
Yeah, there definitely have been proposed signatures of technology or agriculture, anything that suggests that there is life on a very different scale than just microbial. But the probability that we find something like this is probably even lower than that we find primitive life, because it will take billions of years for a society as ours to develop. And then we don't know how long it will actually be there. Mankind was only for a very short time so far on this planet, and we might not be much longer. So Earth have looked like this, the early Earth, with methane and CO2 in the atmosphere and some nitrogen and basically nothing else, and just some microbes being there, was present for billions of years, for the longest bit of Earth's history. So we're mostly focusing on something like this because we'd expect this to be a more likely state that we find a planet in with life.
Yeah, okay, got you. Yes, yes, it's indicative of a very small part of, Earth's history, I guess, isn't it? Hey, you've got a really good question here from John McNichol, and it said, would there be a hope to detect a polar aurora ovals on exoplanets to prove the planet has a magnetic field? Well, that's a great question, I thought.
Yeah. Yes. There's for example, we know that Jupiter has aurora as well, and we can detect it there. So I'm just not quite sure how far we are with looking for that similar observations and similar detections for exoplanets. But there's definitely, we can go in the direction of the radio emission from aurora that we've also received from Jupiter, and to look for similar signs or the molecular lines that are produced in the light from exoplanets. But obviously, the smaller a signal is inside a planet. Like when we look at the exoplanets, we usually only have one pixel for the whole system. So it needs to be detectable in that whole background of the star and planet.
Yeah, okay, great. Hey, a question on phosgene, is it pH3? Can this be inorganic in origin? Question. Or could it be from, a sort of chemical reaction on the surface with clays and iron oxide, for example?
So we know that it exists inorganically, or like abiotically, in, for example, the atmosphere of Jupiter. So in such a reducing atmosphere, we definitely know that there are chemical pathways to phosphine formation. However, on the Earth, we don't know of any way to produce phosphine other than biology in conditions that are present on Earth's surface, or also in the atmosphere of Venus. So there's a lot of work going on of people trying to figure out whether we just missed something, and trying to figure out whether there might actually be some chemical pathway to form it abiotically. But so far, there has nothing been found.
Yeah, I was going to sort of ask myself, is there any chemical that's absolutely indicative? I know you said that carbon monoxide was indicative of there being absolutely nothing because it disappears so quickly where there is something. Is the one, and I guess phosgene was, I guess, pretty close to that, but is there any other chemical that's a really good one?
Yeah, I think phosphine is currently probably the most proposed one, but it is also a very niche one, because even if it is produced by life, the abundances might be extremely low. And so we might not be able to observe it on a planet that's farther away than Venus, especially on exoplanets. So you always have to, you'll find gases or molecules that can only be produced by life when you know roughly the atmospheric composition. But you might need to go down to very rare gases that you won't be able to detect them. So you always need to find the trade-off between abundant enough to be detectable, but also not too common to be produced by too many different pathways.
Yeah, got you. Yeah. So a question here from Pete, actually. What is RNA? That's
RNA is basically the precursor of DNA. It's also similar, and I'm not a biologist here, so it's a very, very rudimentary explanations. It's also used, for example, by as like a carrier for informations, for example, with the COVID vaccine, mRNA vaccines. And it's basically like just one of the strands of the DNA. So like the DNA has this double helix and RNA is just one side of it, but also it has a different nucleobase, I think. Like there are 4 nucleobases and RNA has three are the same as DNA, and then there's a 4th one which is different, I think. But yeah, it's like in this theory, it's assumed to be a precursor of DNA in the origin of life.
yeah, got you. So yes, if you found out, you'd be, well, hey.
Yeah.
That's yeah, okay. That's hey, what do you think is the most likely origin of life on Earth, in your opinion? Is it which one of the 3 ways that you talked about, the hotbed, the warm pond, and the panspermia type of origin?
Yeah, I think it's the most likely is a warm little pond. Like the panspermia is a bit annoying because it just moves the problem away to somewhere else. So we'd still need to explain how life is formed somewhere else if we assume that it is transported to us. And the problem that the hydrothermal vent theory has is that eventually you'll release all your material into the ocean, and the ocean is just gigantic, so it will dissolve very quickly, and so it should be extremely hard to concentrate material. And that's the advantage of having a very small, concise body of water, like such a pond, where you can then concentrate the material. But whether it's in the end the prebiotic molecules delivered from space or produced by lightning in volcanic plumes, and then you have like these warm little ponds on the shores of volcanic islands, I don't know. That's
Yes, I like that thought, actually, because it's you just don't solve the chicken and egg problem with panspermia, do you?
yes.
Yeah, okay. Hey, last question here is what big developments do you think are coming up in your field in the next sort of decade or so? Or are you waiting for a big flagship sort of space launch like the JWST and that sort of?
Yeah, I think the most important next step will be to have a mission that is actually able to observe the abundances of molecules in atmospheres of terrestrial Earth-sized exoplanets. So we'll already get some information from JWST. It won't be able to give us a detailed description of, for example, the TRAPPIST-1 planet atmospheres, but it will definitely give us some rough idea on whether there may be clouds in the atmosphere also, by just the general shape of the spectrum. But it will definitely wait for more missions. It doesn't necessarily need to be a big flagship missions. There are also smaller ones like Ariel. It's an ESA mission, which is launching in the 2030s, that will be able to look more detailed on atmospheric compositions. And then also more exploration of the solar system, where we're sending more and more missions to the icy moons of Jupiter or to Titan, and to look for signs of life, in either extinct life or living life or habitable conditions in the solar system.
Yeah, I guess it's just a question more of us deciding that we need to prioritize this and actually developing clever little ways of doing it, rather than sort of a humongous thing that takes a lot of effort and it is by its nature quite generalistic, isn't it? I guess. Anyway, hey, thanks very much for that, Patrick. It was a great talk, and I'll hand you over to Tim for the vote of thanks. I'll hand over to Tim.
Oh, thanks.
Thanks, Rich, and thanks to you, Patrick, for a really comprehensive talk. I do have just one more question, if you don't mind answering another one, and that is, do you think that a habitable planet needs a moon or moons like the Earth has? Do you think having one or more moons benefits or would benefit a habitable planet?
Yes, so there's definitely, the moon has an stabilizing effect on Earth's orbit and Earth's evolution. So it's definitely something that might be important. Also, when we are thinking about tides, just like the ocean tides, it can be that tidal ponds are just these environments where you have cycles of dry and wet that actually gave us the opportunity, like the ingredients to start life. So maybe if this is actually what happened, maybe then without a moon, without tides, life wouldn't have started. So there are a lot of factors where the moon is definitely beneficial, but I don't think the consensus is that we need to have one.
Thanks very much for answering that. I was thinking while you were giving your talk, I was thinking back to the days when I was a student at your university, St Andrews, which was almost 50 years ago. Goodness me. And even the thought of life on other planets was, almost science fiction then. It certainly wasn't part of the main syllabus, and exoplanets were just not even considered. So it's amazing how here, almost 50 years later, we're talking about these subjects and able to get so much data from, as you say, from a single pixel quite often.
Yeah,
absolutely incredible. So I must thank you for bringing to this talk such an amazing array of information. It really has been fascinating, and we can't thank you enough for giving up your time to talk to us. Do you spend much time in St Andrews, or do you do most of it remotely?
So since I've moved to Austria last autumn, I haven't really been back much. So I'm now mostly working, here at the Institute in Graz. But I'll only be back for my Viva.
Oh, right.
In summer.
Okay.
Then.
Well, hopefully that all goes well, and you may want to celebrate with a glass of whiskey. I don't know if you drink whiskey or
yes. I was on the committee of the Whiskey Society in St.
Oh, well, that is even better, because as a mark of our appreciation for giving up your time to give that fantastic talk, we would like to give you, I don't know if you could see very easily there, a whiskey tumbler, a Sigma whiskey tumbler. It's a very rare item, very collectible, will be worth millions of pounds in the future. So I'll get that, arrange to get that sent to you if you can let Rich have your address where you'd like it to go to. So
thank you very much.
From all of us in Sigma, thank you very much for giving up your time to talk to us, and I'll hand back to Rich. Oh, sorry,
Thank you.
back to Pete.
Thank you very much, Tim. And yeah, thank you, Patrick. It's a fantastic talk. I thought it would be. We have had many talks on exoplanets in the past, but we've not actually had many on what makes them habitable. And that's really, really interesting. So once again, thank you so very, very much for coming along and explaining that.
Yeah. It was a
Okay.
pleasure.
Thank you. Thank you very much. Hopefully we'll get you over here one day when you're back in St. Andrews. Let us know and maybe we can meet up.
What?
Okay. That's great. Okay then, everyone. What we'll do now is we'll head out for the break. Say a quick 10-minute break just to get so we can get reset for the second half. And we were back with the members' photos first. And I say hang around for them because there are some stunners coming in. You will probably have heard there was a bit of an aurora went on last Sunday. I think everyone heard about it from all over the country. We got some brilliant photographs coming in about that and some real good deep sky stuff as well. So hang around and we'll be back in about 10 minutes. Okay, we'll see you then. Oh, just let you know the chat's back on. So if you want to talk to everyone else, you can have a chat. Okay, everybody, welcome back to the second half of the Sigma meeting. Right, so Ray, if you are ready, we'll be going over to the members' photos in a moment, and then after that, we'll be going to Mick with his Moray Sky at Night to show you what's up in the heavens this month. So Ray, if you want to share your screen. Some of you may not have met Ray before. Ray is our latest committee member, Ray Palmer, Dr. Ray Palmer, to give him his proper title. And he's going to show you these wonderful photographs. So over to you, Ray.
Hi, everybody. As Pete said, it's been quite a busy week and for people taking photographs with the a nice display of aurora. Actually, I notice at the moment that at 8 o'clock there's a yellow alert for aurora activity, but if your place is anything like mine, it's just shrouded in grey cloud at the moment, so I don't think there's any chance. But anyway, without much further ado, let's shoot on with the photographs. So the first one is from Mick, and it's a nice scenic shot of Jupiter here, Moon and Venus at the bottom. Nice alignment. What's really nice about this is, as you can you can see the Earthshine, the exposure that Mick's taken actually clearly shows the Earthshine on the Moon. So that's come out really quite well, I think. That's in Lossiemouth, and that was taken on the 22nd of February, as it says here. Well done, Mick. The next one is from somebody I recognise. This is one I took, funnily enough, it's the Heart Nebula, and purely by chance it was taken around about St. Valentine's Day. It's an emission nebula, for those of you who don't know, in Cassiopeia. It's something like 75,000 light years away. The emissions the colours are caused by ionized gas, which is consequently radiation by this small group of stars at the centre here, which the ultraviolet radiation is actually ionizing the surrounding gas. And this area is a star cluster that's known as Melotte 15. And these areas here, dark dust lanes, are thought to be active regions of star formation. So an interesting object. It's quite a big object. I used an ASCAR 300 millimeter focal length astrograph. It's got a 61 millimeter objective, and I used a ASI 2600 MC Pro one-shot cool color camera with an L-Extreme dual band narrowband filter. And this was actually taken during a pretty full moon, a lot of, very bright sky with the full moon. And the effectiveness of this dual band narrowband filter really comes out well, because it completely eliminates any gradient caused by the moon, because you're really only allowing certain wavelengths of light in, the hydrogen alpha and oxygen 3 part of the spectrum. So Heart Nebula. Next one, again, from somebody I recognize. This is the Green Comet, which everybody knows. Again, I took this, I think it was actually in the same night as a Heart Nebula, if I remember rightly. No, it wasn't, it was the next night. And to be honest, it could have done with maybe slightly longer sub-exposures, because I could have, you can just about make out the ion tail here. It maybe would have come out a bit better with maybe longer subs, but I was concerned if I left it longer, you might get a bit of blurring, which we'll see in a minute when I show you an animation I did. The green color, for those of you who don't know, it's caused by the formation and degradation of diatomic carbon. Comets, many comets, in fact, I think Patrick will be able to answer this, actually contain a lot of organic materials. And diatomic carbon is very, very unstable on Earth. And when it breaks down, it emits light at about 525 nanometers, which is basically in the green part of the spectrum, so hence its color. I used a SPRI 120 triplet refractor again with the one-shot color camera, but it's unfiltered this time. This is without any dual band filters or anything. Processed it and picked Sunsight, and as I said, it was a real bugger because I think it took about 8 hours of processing to actually freeze the comet and the stars, so that stars weren't streaked and neither was a comet. So it's quite a bit of a faff with processing, but yeah, I think it worked out all right actually. Right, this leads me on to the next thing. This was the animation I took of the comet. And you can see actually these images were taken over a period of 1 hour 20 minutes. So you can actually see that the thing's actually racing through the sky at quite a rate of knots. It's barreling through the solar system, hence why it changes its location every night over 24 hours. And yeah, I think it's quite a nice little animation. It just shows you, you know, the relative motion. And it's like I say, that it's actually motion causes a problem for astrophotography because it's trying to balance the length of sub-exposure because the things move. And if you make your sub-exposure too long, then the comet's going to end up looking blurred. Anyways, that's that animation there. Okay, so back to the members' photos. This is by Alan Tuff. It's the same thing. It's a green comet. It's a stack of 11 90-second exposures, and you take this with a Canon EOS 5D DLSR prime focus using an ED80 refractor. I think he's captured the ion trail a lot better than I did. And despite relative poor sky transparency, but again, you can see the green comet quite clearly here, the diatomic carbon. Another picture by very similar to, well, similar in as much as it's got the moon, Jupiter and Venus, and of course they're actually aligning. There's going to be quite a close alignment over the next few days if it's not already passed. But again, just quite a nice shot, seeing the crescent moon, Venus, Jupiter there. 1.6D moon, according to Alan there. Nice photograph again. And again by Alan. Plus, yeah, I think this is a crescent moon. Again, there's evidence here of Earthshine, just about visible from his back garden in Elgin on February the 21st. A little bit of cloud there. It actually adds to the photograph, in my opinion. And from Robert Eady, again, taken on the 26th from his house in Glenkindie. That's a 100 second exposure at f/5.5, f/5.9, Williams Optics 61 Zenith Star apochromatic refractor attached to a 760D camera. I think as Pete's going to tell you, we're having a equipment session very soon. So I think we'll bring along some of this stuff so that for those of you that are unfamiliar with these terms or these pieces of equipment, you can have a look yourself. Be a worthwhile exercise. Yeah, again, nice view of a half moon here. Just about catch the edge of the Pennine Mountains around a bit here. Yep, very nice. Again from Alan. Again, we've got the green comet, and with Mars. And again, he's used the EOS 5D and Sigma 150mm telephoto lens with an Ultron Star Tracker Pro. He said there was a lot of as you can see, there's a lot of high-level cloud around that night, and like a lot of astrophotography, it's a question of trying to get an image in between cloud cover. So well done. This is from Pete. There was a bit of a scramble, I think, the 22nd of February this week. Last week, sorry. Is it this week? Yes, this week. Sorry, I beg your pardon. I've lost track of the days. And it's, I think everybody found out it was a nice display in clear skies. Everybody reached for their cameras and fled outdoors. So this was taken from Kingston and the Moray Firth. Again, 1200D camera, ISO 1600, f4, 8-second exposure. Again, very nice composition here with stuff in the foreground, the water, stars. Same thing, again by Pete. You've got the aurora pillars showing quite nicely here. Again, from what I remember of watching it, it was changing from minute to minute. It was brightening, it was dimming. You're getting lots of different forms of the aurora occurring. Very nice again. Nice composition with the stars. And I think this one as well, again from Pete over Lossiemouth, the moon in conjunction with the Pleiades over here. Got the Pleiades here and the moon, and again, aurora. And, where are we? Sorry, beg your pardon. Auroral arches was raised looking towards Buckie, and it stretched from horizon to horizon from Buckie to Lossiemouth. So again, it shows you the extent of the display actually. Well done, Pete. This is mine. It was taken from a back garden here in Mostowie. Use a Canon 200D with an 18 to 55mm zoom at 35mm focal length. Again, I only used a 3-second exposure. I forget what the ISO was, but I put it up quite high. But again, got some nice pillars there, I felt. So yeah, very pleased with that photograph. So all in all, great week for seeing aurora. Again, more from Alan. So for 400 photographs on Sunday night. So it's as he says, it's taken him a while to sort them all out. This was taken from Hopton Beach again with his EOS 5D and his Sigma 20mm lens, so it's more wide field. Exposure 6 seconds this time, f3.2 and an ISO 1600. Very nice photograph indeed. It captures the colours brilliantly and I love the reflections in the water as well. Okay, that's it. That's it for me and the members' photos. So I think it's over to Mick now for the Moray sky at night.
Thanks very much, Ray. Let me just there we go. You should be able to see that, can you? All good. Just get rid of some stuff here. Okay. Good evening all. Welcome to Sigma's March 2023 edition of the Moray Sky at Night. So my night sky guide tonight is going to supplement what's in this month's newsletter, and I'll start with this month's planets and moon as usual, and I'll follow that up with a tour of, well, it's in a constellation actually, and finish off with what could be the final words on this green comet. So some possible photo opportunities this month. So this evening, this was tonight at 6 o'clock. if there hadn't been any clouds. And you might remember that I mentioned last month, and Ray's just mentioned it actually as well. If I rewind a few days, if you keep an eye on Jupiter and Venus, so they were starting to approach 28th, and they've actually passed now, and they're starting to separate. So you can catch them over the next couple of nights if it's clear, before they separate much more, and just after sunset and just before these two set. And tonight as well, the moon is the almost full moon is just to the east of Pollux. Moving forward to the 6th, I need to go to which one? Yeah, the moon is 4.5 degrees to the east of Regulus. Forward to the 10th. A bit later to catch it. The moon is just to the east of Spica. On the 15th, Neptune, our outer planet, is going to be at superior conjunction. So that's on the other side of the Sun. On the 17th, Mercury will be superior conjunction. So that's the other side of the Sun as well. On the 20th, nothing much to see at the minute, but on the 20th is vernal equinox. So that's the moment that the Sun crosses the celestial equator, moving from south to north. And that marks the first day of spring. So that's the 20th of March. And it's often referred to as the spring equinox. On 22nd, 22nd, my time's here, 18. So again, just after sunset on the 22nd, the new moon is going to be passing Jupiter and Venus, 23rd to 24th. The 24th is going to be right next to Uranus. The 26th, so Sunday the 26th of March, the clocks go forward an hour at 1 AM to 2 AM, and that's for the start of British summertime. And 26th, the moon is passing by, well, just to the north of Aldebaran and just passing the Pleiades. And it's 27th, 28th, it's going to be passing Mars. And then a first quarter moon will just be passing by Pollux in Gemini on the 29th, 30th. So that's that for now. So now we're going to have a look at around the muddy night sky, and I'm going to start by revisiting. Let me just get set up here. We'll go to the middle of the month. 1900. I'm going to start by revisiting, for the sake of a few new members who are here tonight, and a bit of a recap for the rest of you. The big G of the winter sky, which are taken from Bill Leslie's Winter Sky Notes. Bill Leslie, for those who don't know, is one of our presidents of Sigma, and he put together a series of sky notes. So this is a great way to find your way around the night sky. And on your way, you'll find out about some dominant constellations this time of year and the names of some of the brightest stars. Now you can look for this just after sunset. If I put the atmosphere on, you can see that these brighter stars are easier to find. So if you go out and start having a look, for those of you who are new and try to find your way around the sky, if you go out just after sunset and watch what starts to appear in the sky, that'll give you a good idea to start finding your way around, because you can see a lot better these stars than when it's darker. They sort of start to merge with a lot of the other ones. So I'll leave it like this actually. So what we'll do is to look into the south, so the middle of the month, about 7 PM. And standing out, you've got the three stars that make up the belt of Orion. They're fairly obvious. So this big G, if you follow these three stars up about 20 degrees, you'll find this red giant star, Aldebaran. This sits in the Hyades within Taurus, constellation of Taurus here. I'll just put the lines on for you to see. So this is the start of the big G, as if you were writing a G. So from Aldebaran, we continue, go straight north about another 20 odd degrees, and you find Capella, a very bright star. This sits in Auriga, a pentangle of Auriga, although Stellarium here is draw it and put an extra point in it. And you'll notice that there's a star here which is shared with Taurus and Auriga. Beta Tauri, 23 Auriga. So that's the start of the G. So we'll go up here, and then coming down the other side, we have Castor and Pollux, which sit in Gemini, the twins. And then heading back south into a kind of barren part of the sky, there's not a lot to see around here really, apart from this bright star Procyon, which sits in Canis Minor, the little dog, the small dog. And continue down to the brightest star in the sky, Sirius. Oh, not that one, that one. Oh, go away. Sirius, this is in Canis Major, the large dog. This is a dog star. As I say, it's the brightest star in the sky. So where have we gone from? Aldebaran, Capella, coming round, Castor Pollux, Procyon, Sirius. And we head back up to Rigel at the southwestern foot of Orion, and then up to Bellatrix and across to Betelgeuse. And so that makes up your big G of the winter sky. So straight away, you've got a whole selection of constellations to get you started to start finding your way around. Betelgeuse, incidentally, is a red giant, and it's so massive. Of course, the sun is just set over here. It's so massive that if it replaced the sun, it would completely swamp out Venus, Earth, and it would almost reach out to Jupiter away out there. It's that big. So tonight we're going to have a closer look at Gemini, the twins. So this is one of the most prominent and sought after or sought out constellations in the northern sky during the winter. Deep sky observers and imagers are spoiled by an abundance of bright, colourful targets. As you see, it lies to the northwest of Orion, and it shares its boundary, its northern boundary, with Auriga, Auriga's southern boundary. I'll put the boundaries up so you can see the constellation boundaries in red here. So Gemini's main stars form a rectangular shape, some 20 degrees in length along the major axis, orientated northeast to southwest. And this asterism, or star pattern, is dominated by the bright stars Castor and Pollux. Quite an unmistakable pair, as I showed you when I did the big G, that lie 4.5 degrees apart at Gemini's eastern end. So these culminate around 60 degrees in altitude in the middle of this month, around 9 p.m. So pretty easy to find, nice and high. Gemini is one of the original 48 constellations described by the 2nd century AD Greek astronomer and mathematician Ptolemy. It's also one of the 12 zodiacal constellations, and in 2023, the sun passes through Gemini from the 22nd of June to the 21st of July. So Pollux, a yellow-orange class K03 giant, shines at a magnitude of 1.15, and it's the brighter of the pair, although it was relegated to Gemini's beta designation by Bayer. It's just 34 light years from Earth, and it's the closest giant to the Sun. Since 1943, the spectrum of this star has served as one of the stable anchor points by which other stars are classified. In 2006, an extrasolar planet designated Pollux little b with a mass of at least 2.3 times that of Jupiter was confirmed to be orbiting Pollux with an orbital period of 590 days. And in December 2015, the planet was named as Thestius. Castor Alpha Geminorum is one of the best double stars for a small telescope and an amazing sextuplet star for professional studies. To the naked eye, it's a bright star shining at a magnitude of 1.58. Stellium differs to that. But turn even a small telescope around 3 inches or 80 millimeters in its direction with 100 times power, and you'll be able to split Castor into 2 single points of light. The brightest Castor A is a magnitude 1.93 A-class star, and it is a magnitude 2.97 Castor B, another A-class star, which lies to its northeast. They take almost 445 years to slowly encircle one another, and presently the pair have widened to the closest separation of about 1.8 minutes to a current separation of around 4.5 minutes. So both Castor A and B are not one star, but 2. And from the spectral lines, Castor A little b is a cool low mass K-class star, and Castor B little b is an even cooler M red dwarf. Both are spectroscopic binaries and they can't be split visually. Castor C, another spectroscopic binary, shows a reddish tint on a small telescope, and it shines at a magnitude of 9.8, and it lies 70 seconds south of Castor A. So, to see some other stuff in Gemini, come on, what's happening? Speeding up. I'm a bit Pete Tong here. Okay, so if we head from Castor just 3 degrees southwest to about here. Zoom in a bit. There we go. Find NGC 2371 and 2372. So this is quite a challenging planetary nebula for a medium aperture telescope. It's got a curious double lobe structure in common with the Little Dumbbell Nebula, Messier 76, and Perseus, albeit appearing significantly fainter. William Herschel saw a separate nebula, and John Dreyer added 2 entries in the New General Catalogue. So it's only showing 2371 on here, but it's classed as 2371 and 2372. So they can be captured as a faint, hazy smudge of light through a 6-inch telescope. But to glimpse it as 2 patches of light, you're probably going to require a 10-inch telescope, 250 millimeters, with a no-3 filter. Try to observe it at a site free from major light pollution on a transparent night. So the moon is new on the 21st of March this year. So a few nights either side of the 21st, and you should be pretty good to try for that, clouds permitting, obviously. Right, our next 2 targets lie a short hop from magnitude 3.3 Propus. So if we continue down Castor to its leg and down its foot, we find Tejat, Propus, and 1 gem. Propus is worth a few minutes having a look at. It's a tight and unequal binary star and a variable star, best known as a semi-regular with a brightness range of about half a magnitude. It is, however, also an eclipsing binary with a period of about 8 years and 2 months. A fascinating object lies on its doorstep. A mere half a degree to the east, we can find IC443, the Jellyfish Nebula. This is the shredded remains of a massive star that went supernova and blasted itself apart between 3,000 and 30,000 years ago. Visually, it's pretty tough to observe, even if it's easy to locate, because it's afflicted with low surface brightness, and its eerie light is spread over 50 minutes, much larger than the full moon diameter. From a dark site, a telescope around 12-inch or 300 millimeters, operating with a low power eyepiece and an O3 filter might snare it on a transparent and moonless night. but if you have any high level haze, it's going to make it a bit tougher. Imagers, though, routinely produce incredible shots of it, especially wide field narrowband portraits. So next we head to Messier 35, Gemini's top build open cluster, and its only Messier designated object. It's arguably the best in its class in the winter sky outside of the Pleiades, and it's easy to find just 2.5 degrees northwest of Propus. So just here, if you're in a dark enough site, you should be able to see these with the naked eye. If you stick a pair of binoculars on it, they should stand out pretty well. I say not quite as good as the Pleiades, but it's up there. So we've got an integrated magnitude of 5.1. A pair of binoculars, you should be able to see about 30 or so stars against the nebulous background of collective light from the masses of unresolved stars. So it's a large cluster, small telescope revealing an apparent diameter of 28 minutes and maybe 40 or so cluster members. It's a relatively young open cluster, believed to have formed around 100 to 150 million years ago. If you're observing it through at least a 6-inch telescope, though, you should be able to spot just 20 minutes to the south, NGC 2158. Which apparently looks quite yellow when you look at it. I haven't looked at it myself, but it's one of the most ancient open clusters, and it could be mistaken for a globular cluster. This is thought to have formed an amazing 2 billion years ago. While in this area, if you've got a large telescope as well, you might be able to pick out a couple of open clusters. IC 2157 and IC 2156. So a penultimate stopping point is NGC 2392, a bright and famous planetary nebula known primarily as a clown-faced nebula. What I'm going to do is take away this for a second. So moving away from Castor onto Pollux, if we come down to the west star here, Wasat, Delta Geminid, and let me get orientated here, right. Yeah, I've got it, I think. Right, if you head to the south here, southwest, you see this triangle of stars. If you take these two stars and just about a third of the way down, across to this one, I hope I've got it. Just below that, yeah, there's the Eskimo Nebula, or the Clown-Faced Nebula. Hubble Space Telescope images down the decades have made it an iconic object that's arguably Gemini's outstanding deep sky target. It's got high surface brightness, making it one of the easier planetary nebula to find and observe in a small telescope, shining at a magnitude of 9.2. It varies a bit on stellarium, but it appears as a distinctly bluish-green fuzzy star through a 3 to 4 inch refractor at low power. Increasing the magnification helps it to stand out more easily from field stars and can reveal a bright core. If you go up to a 10 to a 12 inch telescope operating at a magnification of around 150, that'll show the fainter outer halo, especially with a no-3 filter in place, and also the 10th magnitude central star. Okay, I'm going to end tonight's tour of Gemini with this month's object challenge. So this is Abell 21 we're going to look at, another planetary nebula. So it's a different beast. probably descriptive term, is it's far better known as the Medusa Nebula. So it's located in Gemini's far southern region. Well, I just happen to have left the borders up. So down here, I think one of these is supposed to find it. If you head to Procyon, we come up to the other star, Gomesa, that makes up Canis Minor, and head north to this star here, and then just a small hop. No, not to that one. It's in here. Come here. Oh, it's just going to annoy me now. There we go. It's in here. So this is an imaging favourite, but a tough visual target. It's a large crescent-shaped nebula with its light spread over 10 by 6 minutes, making it difficult to distinguish from the night sky background. Under typical UK conditions, it's likely you're going to need a 12-inch telescope to see it, even with the aid of an O3 filter. But if you're observing from a dark site on a fine night, then have a go with a smaller size telescope. So that ends my tour. I'll just quickly mention meteors. There are no major meteor showers this month. And as Ray mentioned about the comet, the green comet that we've been talking about the past few months, this is now fading fast and it's no longer a circumpolar object. So if you want to keep track of it, I did send out a track in the newsletter, so you've got a rough idea where it's going over the next month. But if you want to keep an eye on it, I'd recommend heavensabove.com or the other one, inthesky.org. And if you put your location in there, it'll give you good up-to-date information on that and many other things, actually. So that's me for tonight, Pete, and for this month. So I'll see you all back in September for the next Sky at Night.
Yep, that's great, Mick. So yeah, as you say, that's going to be the last one for this season, because when we get into April, the sky is going to be too light, isn't it?
Yeah.
So, but you will be happy to know that Stuart will be back with his space news then. So something to look forward to. Right, I'll just finish off with a little bit of the club news. As Ray mentioned earlier, and I put it in the newsletter as well, that I was planning to do a telescope workshop. Well, we call it a telescope and equipment workshop. Okay. I was planning on the 1st of April. You'll be pleased to know I've been in touch with the hall. The small hall is free that day. So I've got it booked from 11 o'clock until 1. So we can all get together, bring your telescopes down or any equipment you've got. You know, if you've got any questions you've got or any difficulties you've got using it, you can ask us and we'll try and sort it out for you. Let's say, even if you haven't got telescopes and you just want to come down, it's a nice chance for us to just get together in social, you know, in a social environment, and even have a couple, you know, we'll have the kitchen open and the teas and coffees running as well. So, and hopefully, if the weather gods are nice to us, we can, and the sun's shining, we'll get some solar observing done afterwards, or even during. So something to look forward to. That's on Saturday, the 1st of April, at 11 o'clock, and that's at Lambride. Okay. So any new members who haven't been to a Sigma meeting before and you not quite sure where we meet, come on down on a Saturday. You can see it in the daylight. Yeah, next month's meeting. Just before we go to next month's meeting, I'll tell you, because this was meant to have been our final Zoom session for most of this year, but our speaker for May, he couldn't make it up on the Friday, but he's got family sort of ties. It means he's got to be back in Leicester on the Saturday. So therefore, we decided that what we'll do is we'll actually do a Zoom meeting for the May meeting, you know, rather than mess our speaker around. So we will be having another Zoom meeting in May. But next month's meeting is a physical meeting, and that's on the 7th of April. That's Anne-Marie Wisemans from the University of St Andrews again, with the Sloan Digital Survey. In this talk, Anne-Marie will be discussing the history and technological developments of the Sloan Digital Survey and highlights and the discoveries that is made. Okay, so that is on the 7th of April, Friday. Doors open at 7 for a 7:30 start. Say normally have the teas and coffees running beforehand as well. Very important part of Sigma, that the teas and coffees and good old chat. It'd be strange having to get you all to sit down again, ready to start the meetings and then like this. Yeah, don't forget our telescopes are still for hire if you want them. Let me or Rich know and we'll get organised to meet up. To say we've got the Skywatcher and the Helios. Please come and use them. And say by the time we get to the middle of April, there's going to be very, very little daylight. Sorry, nighttime left, and the daylight will be taking over. I know some of you came in a bit late on this talk, work commitments and the like. Don't worry. I would hope for you by the end of the weekend have it edited. We'll have it up on the YouTube channel, and I will send the link out to you on there. On email, I'll send you the link by email because it will be for members only for a few months. Don't forget, if you've got anything for me, just let me know. Ping me an email, and we'll see what we can do for you. We said it's your club, it's not my club or the committee's club, it's your club. Well, it's all of our club, actually. And next month, obviously, is a good time to invite a friend along to Sigma. So say physical meeting, just grab them by the scruff of the neck and say, right, you're coming with me tonight, come have a look at this, okay? It's all down at Lambride. The first meeting is always free, as you know yourself, and then if they like it, they can join them. Okay. So with that, I think that's about everything. There's not that much club news. As I say, we've not been getting out that much apart from last Sunday when everybody was out and WhatsApp was pinging like mad because the sky lit up. Let's say that WhatsApp, if you haven't joined the WhatsApp group, I would say do it because it's a really good way for us all to keep together. And once one member sees something in the sky, everyone knows about it and we all get out. Okay, so with that, as I say, I want to thank Patrick for his wonderful talk. It was absolutely superb. Really interesting actually. Rich for handling the Q&As. Tim for doing that vote of thanks, and it's quite strange how many astronomers also like a little bit of whiskey in a whiskey glass, isn't it? Ray done a wonderful job with the members' photos. I think you might have a permanent job there. Let's see, Mick Freemore Sky at Night. That was a great way to end the year. Some challenging targets there, but if you don't have a go, you'll never know. Eskimo Nebula is quite challenging, but when you see it, it's quite amazing. So have a go at that one at least. And I want to thank you all for coming along as well. We good selves, as I say, it makes the night, and we had a good turnout again tonight. And with that is, thank you very much, and we will see you soon. Keep looking up and keep looking on. Good night, everybody.